Hello everyone, welcome. In this video we will explore the generator differential protection or 87G, which protects the generator from internal faults. It works by comparing currents at both ends of the generator to detect any differences. The protection is designed to be sensitive enough to catch internal faults while remaining secure and restrained against external faults. From CT errors or throw currents, we will also look at the key concepts like the bias current, the minimum backup for differential current, and the slope settings that ensure a reliable operation. So let us dive in. So as you can see from the screen, the generator differential relay will normally trip the generator or the generator step-up transformer breaker, the field breakers, and initiate an immediate shutdown of the prime mover. So usually a simplified relay, like it's used for transformer differential protection without the inrush blocking and vector group correction is applied. The simplest form of the differential protection is provided by an instantaneous relay connected as shown in the left figure. The direction of the current flow shown is for load or for a fault outside of the differential zone of protection, assuming ideal current transformer CTs are current I1 and I2, and it will be identical, and the relay operating current I0 will be 0. Where the fault occurs within the differential zone of protection as shown in the right figure, the current in one CT will reverse and the relay current is the full short circuit current as reflected by the CT ratio, so I0 will equal to I1 plus I2. It's important to note that the differential scheme will not detect the turn-to-turn fault within the stator phase winding. This type of failure may cause dissimilar phase currents, but because the current in each differential CT will be equal, the relay will not detect the fault. So normally for the generator more than 5 megavolt ampere, if the fault occurs inside the protected area, the differential current Idiff is calculated unequal 0. So the I differential will equal to I fault. But if a load current flows through the protected area or external fault conditions, the differential current I differential is calculated to be 0. So the result here, the calculated value of the Idiff is sufficient to distinguish between a short circuit current inside or outside the protected area or a flowing through load current. So here is the percentage differential relay, and the main advantages of the percentage differential relays is the first one is it's designed to overcome the CT error limitations in the differential protection. So the traditional differential schemes can misoperate under external high current faults due to the CT saturation. Percentage differential relay are developed to add stabilizing element that prevents such mal-operation. Also, the relay measures the current imbalance and compare it to the threshold proportional to the total current flowing. So only if the differential current exceeds this threshold, the relay will issue a trip command. Additionally, the principle ensures that the relay remains stable, doesn't operate or doesn't trip during the external faults with CT errors, while still detecting and responding quickly to internal fault. The slope of or the percentage defines how much higher the differential current must be in relation to the restraint current. For example, a slope of 20% means the differential current must exceed 20% of the average current to trigger the operation. Also, restraint current may be calculated as I1 plus I2 divided by 2, or the absolute of I1 plus the absolute of I2, or the maximum of I1 and I2. So it's essential to understand the relay specific logic when setting or testing this relays based on the relay manufacturer. Last but not least, also the principle originated from the electromechanical design, but it has been widely adopted in the digital relays for its effectiveness and flexibility, often with programmable characteristic and self-adaptive setting. So the phase differential protection or the 87 phase element is designed to detect internal faults within the generator stator wind. These faults often occur when a phase to neutral fault is not cleared quickly, allowing the damage to spread. So if such fault persists, it can lead to severe overheating and usually result in the destruction of the stator. That's why the differential protection is one of the most critical and sensitive protection schemes for generators. Even after the generator breaks, opens, and both the field excitation and the prime mover are tripped, the current doesn't stop immediately. So the generator's magnetic field continues to collapse, and the machine keeps rotating for a short time, which allows current to keep flowing until the rotor fully stops. This residual current can still cause additional damage if a fault exists. So fast and reliable protection is essential to limit this impact. As we can see in this figure, even after the breaker opens, and pulse the field and prime mover are tripped, current continues to flow for a short period. And this happens because the generator magnetic field and rotor inertia doesn't collapse instantly, as we said. So the machine gradually slows down and the current decays until it comes to a complete stop. So you can see from the figure here is the fault inception, and the high side breaker opens and the current still flowing. In the generator protection, the main defense against stator phase fault is the 87 phase differential protection, which quickly detects internal faults. As a backup, we use the other elements like the phase and ground over current protection, the 50, 50N, and 51N functions, which operates over a wide range of frequency from 8 up to 80 Hz, and this allows them to protect the generator even during the startup and shutdown when frequency is low. And additionally, the 51V element or voltage restraint over current protection provides additional backup by adjusting its sensitivity as a voltage and current decreases. So it can also be used alongside the distance element 21. So together, these functions ensure a reliable protection and proper fault coverage throughout all operating conditions. So the key design points for 87G, which is a generator differential protection, focus on both sensitivity and security. So the relay must be sensitive enough to detect fault occurring inside the protected zone while remaining secure against false trips, especially those caused by the CT saturation. It also needs to operate correctly at off nominal frequency, such as during the generator startup, to ensure protection from internal faults. Finally, the differential characteristic often uses a variable percentage slope, which allows a balance between sensitivity to real internal faults and restraint against measurement errors or through faults. So the 87G used to protect for three-phase faults, line-to-line faults, phase-to-ground faults, and may not be able to detect a single phase-to-ground fault on high-impedance grounded generators. So restraint or percentage differential trip characteristic used to improve sensitivity for detecting small levels of fault current and also maintain security against inadvertent tripping due to through faults. As you can see here, is the differential protection works by comparing the currents measured at the terminal end CTs with the current at the neutral end CTs. It normally provides three zones of protection to ensure both sensitivity and reliability. The first is the minimum pickup, which reduces sensitivity at low power levels to prevent unnecessary tripping. The second, slope 1, compensates for any errors in the CT to ensure accurate fault detection. The third, which is the slope 2, is less sensitive and is designed to handle CT saturations that can occur during through fault conditions. Together, these zones ensure that the differential protection operates effectively under a wide range of operating conditions. The minimum operating current setting for a generator differential protection must be above the maximum expected differential error current at the restraint or the bias current. For example, at 5 ampere bias current, if one CT is plus 2% and the other is minus 2%, so the net error is 4% given an operating current of 0.2 ampere. So a setting at or above this value is usually sufficient, and setting below 0.1 are not recommended at all. So the differential protection characteristic is defined by the differential current Idiff and the stabilizing or bias current Ibias, which accounts for CT errors and saturation. The operating characteristic must always exceed the summation of expected errors to reliably distinguish between the blocking and the tripping conditions, using a low slope to improve the sensitivity to evolving insulation failures and detecting small leakage currents before they escalate. But the slope must balance sensitivity and security to avoid false trips. Here is the calculation of the Ibias current, which can differ depending on the protection device and the manufacturer in use. So the bias current is often called stabilizing or restraint current, and the operating characteristic for generator differential protection represents the relation between the differential current Idiff and the stabilizing current or biasing current Ibias. So the I differential is the summation or the vectorial summation of I side 1 current and I side 2 current, but on the other hand, the Ibias is the mathematical summation of I side 1 plus I side 2. However, in order to account for a CT saturation and for CT measurement errors due to the CT tolerances, it's not sufficient to only consider the differential current Idiff, as several of those errors are dependent on the current magnitude. This parameter needs to be considered as well. For this purpose, the stabilizing current Ibias is defined, and it's purely a mathematical variable that quantifies the loading of the respective generator. So the operating characteristic must be configured so that it's always greater than the summation of the occurring errors, thus enabling the relay to determine or to differentiate between the blocking and the operating state. So here is the how to test the generator differential protection 87G. As you can see from our example, we have here the test object, which is a generator 10.5 kilovolt, 2.5 megavolt ampere, and the other side also is 10.5 kV. And we have 2 CT at both ends, with having a ratio 150/1, so we can calculate the rated current in both sides, and we can define the characteristic curve parameters. As you can see from the right screen here, the setting of the Siemens relay 7UM. So the pickup value for the differential current is equal to 0.1. The Idiff double greater, which is the high set, equal to 3.5 ampere, and also we have the slope 1 equal to 0.25. The base point for slope 1 starting from the origin, which means 0, the slope 2 equal to 0.5, and the base point of slope 2 equal to 2.5, and the time delay for the Idiff greater and Idiff double greater is equal to 0. So here is a test object which need to be configured by the REU function differential. But if you are using our PTL for this relay, just you can simply import the relay parameter setting, and it will be converted to the REU file using the XREU converter. So you can see from the protected object tab here, we are selecting the protected object to be a generator, and we can define the side 1 and side 2. We can define the nominal voltage and the nominal power for each sides. And on the right hand screen, which is the CT tab, we can define the CT ratio in both sides, which is equal to 150 amp over 1, and the start point grounding here, which is towards the protected object, which is towards the generator. And here is the protection device tab. As you can see, the Ibias calculation, and here is the definition of the Ibias calculation. Depends only on the relay manufacturer, which in our case here it's a Siemens relay. So the Ibias equation equal to I primary plus I secondary over K1, and K1 equal to 1. And also you can see the Idiff greater equal to 0.1, Idiff double greater equal to 3.5 IN, and here is the current tolerance in relative and in absolute values. Also the same way also for the time tolerance, and you can see the reference winding is side 1 in this case. On the other hand, you can see the characteristic definition, which is starting from 0.00, which is the origin, to 5 and 1.25, and here is the dual slope characteristic, which is a relation between the Ibias on the horizontal axis and the I differential on the vertical axis. And in the next slides, I will show you how to calculate, if you are starting from scratch, how to calculate these points and how to draw it point by point. So if we can simplify the dual slope characteristic by 3 points, so point 1 will be equal to 0 and 0, which is the origin. Point 2, there is we need to calculate the Idiff and the I bias from the slope equation. Point 3, we have the Idiff double greater, which is equal to 3.5, but we need to calculate the I bias at this value. So to draw the straight line, we need to define each point. So for the point 2, we doesn't have the Idiff value and the I bias value. Both of them are variable, but point 2 is considered at the end of slope 1 and the start of slope 2. So we can define the two equations, and we can make the two equations equal to each other. As you can see, 0.25 I bias equal to 0.5 I bias minus 2.5, which is base point 2. So we can get the I bias value from these two equations. Then we can substitute by I bias value equal to 5 in each one of them to get the Idiff, which is equal to 1.25. And also for the point 3, we know the equation, which is Idiff equal to 0.5 multiplied by I bias minus 2.5. And we know already the I differential, which is equal to Idiff double greater 3.5. So we can calculate the I bias to be 9.5. So we can draw it from scratch. But if you are using the PTT, once you import the relay parameter setting, you will find the dual slope characteristic ready-made in the REU file. So first test, as you can see, we need to test the stability test. First of all, in the left screen, we have to define the local hardware configuration. And in our example, the current system A, S1, is mapped to I primary L1, I primary L2, I primary L3. And the current system P, S2, is mapped to I secondary L1, I secondary L2, and I secondary L3. And we have also one trip command must be mapped to the binary input of the CMC. Also, the voltage transformer circuit breaker tripping signal must be wired to a binary input of the protection relay. First, a stability test for the generator differential protection is performed using the differential configuration module, as you can see from the right hand screen, and you have to define the test module settings, and this configuration test is always performed with an external fault to check the stability against external fault, as you can see from here. So in the test view of the differential configuration module, the fault is located outside the generator and the supply comes from the network side, and also the test is running for can be running for 500 seconds, for example, so that the testing engineer can assess the measurement result within this time. Here is the test is performed with the fault type L1, L2, L3, which is a three-phase fault, and the nominal current, but you are free to select each of the fault type or the fault loops from here. And while the test quantities are applied, the Idiff and the Ibias values have to be read from the relay and have to be entered manually here, as you can see, to be printed out in your test report. So finally, the test has to be assessed manually, as you can see from here. If you are sure that the relay is stable against this kind of external fault, you can click bust. And also you can use the VT-MCB trip, as you can see from the right hand figure here, to block the under-voltage protection function. Also the reset thermal can be used also to permanently reset the thermal storage of the overload protection. So now we will talk about the second test, which is the differential protection characteristic test, as you can see by the advanced differential module. So by using the same local hardware configuration, we will insert the differential operating characteristic module to be used to test the tripping characteristics. So all fault types also applicable. You can select any of the fault type or the fault loops, but for unsymmetrical faults, it's necessary to take possible parallel tripping into consideration, which can be caused by the unbalanced load protection or the definite time over current protection, for example, if it's wired to the same trip contact. Also, you can define here the trip contact to as a trigger condition. The third one, which is the differential trip time test by the differential trip time characteristic module in the test universe. You can put different test shots, as you can see. So first test shot, for example, to test the TI diff greater, and second one for TI diff double greater, which normally it's instantaneous from 0 to 50 milliseconds, and both test points are defined for the fault type L1, L2, L3 in our case, but you are free to select any kind of fault loop. Thank you.